These 5 dots are 5 houses. Horizontal position is house size. Vertical position is price. This blue line is our machine's current guess. For any house size, the line predicts a price. The small red gaps show how far those predictions are from the real prices. We combine those gaps into one mistake score, 0.64. Lower is better. In the last episode, we learned how to measure wrongness. Today, we have one new question. How can the machine change this line so the mistake becomes smaller? For now, the line has only one adjustable knob, its tilt. We call that knob the weight. The current weight is 1.2. First, make the line a little flatter. The predictions move farther from the dots, and the mistake score rises to 1.00. Put it back. Now, make the line a little steeper. The gaps shrink, and the score falls to 0.36. If you were the machine, would you make the line flatter or steeper next? Pause and decide. The steeper nudge gave the smaller mistake, so steeper is the useful direction here. We still have not found the best line, but we learned something reusable. Make the line a little steeper again. The weight becomes 1.6 and the score falls to 0.16. Make it steeper once more. Weight 1.8. Score 0.04. One final small change lands at weight 2, where the line fits these examples and the score reaches 0. We did not test every possible line. Each nearby test told us what to try next. Say the strategy in your own words. Here is the simple version. Make a small change, measure the mistake, keep moving in the direction that makes the mistake smaller, and repeat. Now let us record the same journey on a second graph. Along the bottom, write the weight we tried. Up the side, write its mistake score, which we call loss. Weight 1.2 had loss 0.64. 1.4 had 0.36. 1.6 had 0.16. Keep plotting the attempts, and the dots form a bowl-shaped curve. This is the loss curve. It is not a magical landscape that appeared from nowhere. We built it from the prediction lines and mistake scores you already saw. Every position on this curve represents one possible prediction line. Look at the full U-shaped curve near weight 1.2. If the weight moves right, the loss moves down. Mathematics calls that local tilt the slope. Here the slope is negative, so increasing the weight lowers the loss. Now look at the right side of the same curve. There the slope is positive. Moving right would raise the loss, so downhill means moving left. Downhill is not a fixed screen direction, and it does not always mean making the weight smaller. It means whichever direction reduces loss. Measure the local slope. Move opposite the rise, then measure again. You invented this strategy before hearing its name. It is called gradient descent, a sequence of controlled corrections that lowers loss. Keep that same graph in view, because the equation is only a precise caption for its movement. New weight equals old weight minus learning rate times slope. The blue marker at 1.2 is the old weight. The tangent is the local slope, negative 1.6. The minus sign turns the uphill clue around. The learning rate, 0.125, controls the length of the green step. Now substitute the numbers. 1.2 minus 0.125 times negative 1.6 gives 1.4. Watch the marker move from 1.2 to 1.4. while loss falls from 0.64 to 0.36. Every symbol points to something already visible. Nothing needs to be memorized yet. The direction can be correct, while the step size is still wrong. All three markers start at the same place on the same full U-shaped curve. First, use a tiny learning rate. The marker improves, but only through many closely packed steps. The iteration counter races while the marker barely travels. Tiny works, but it is painfully slow. Next, use a huge learning rate. The marker jumps across the minimum, lands on the other side of the same curve, then jumps back even farther. It oscillates and can escape. Finally, use a balanced learning rate. It does not magically reach the bottom in one shot. It takes several controlled steps with lower loss after each one. Pause and choose which path learns well. The useful step is large enough to make progress and small enough to remain controlled. Now make the code repeat the mechanism you own. Start with a weight. Predict house prices. Measure the loss. Calculate the local slope. Propose a controlled update. Then run the loop again. Watch each code line change the same picture. The prediction line rotates smoothly. The residual gaps shrink, the weight changes, and the loss marker advances. The loop does not run forever. It stops when the slope is almost zero, or when another step produces almost no improvement. But what if a proposed step makes loss larger? Basic gradient descent does not automatically undo it. We can add a safety check. Try the step, compare the new loss, reject it if it is worse. Reduce the learning rate, and retry. After you see that recovery, we can name the safeguard backtracking line search. Our U-shaped curve was chosen because it makes the learning rule easy to see. Real loss landscapes are not always one smooth bowl. Some contain flat regions, narrow valleys, bumps, or several low points. Gradient descent does not see the whole landscape. It only reads the local slope where it is standing. That local clue may lead to a nearby low point rather than the lowest point anywhere. A flat region can also make the slope tiny before the model has found the best answer. So the stopping rule means improvement has become negligible. Not that we have proved this is the best possible model. Keep the intuition, but keep the limitation too. Slope is a local clue, not a map of the whole world. Let us test whether the idea belongs to you, rather than to the house example. A fruit seller predicts a mango's price from its weight. The current prediction line is too steep. A small increase in the model's weight makes the mistake score larger. Should the model's weight increase or decrease on the next step? Pause and decide. It should decrease, because downhill on this side means moving left. Houses and mangoes use different measurements and different prices, but the learning loop survives. Predict, measure the mistake, find which nearby direction lowers it. Take a controlled step, check that loss improved, and repeat. Return to a real house. Price may depend on floor area, bedrooms, age, and location. The model gives each feature its own importance knob. Together, those weighted clues produce one predicted price, and that prediction produces one final loss. If the prediction is wrong, which knob deserves more change? Did floor area contribute too much? Did age contribute too little? For every knob, we still ask the familiar question. If this one changes a little, how does the final loss change? Put those slope answers together, and we call the collection a gradient. But one mystery remains. How can one final mistake send a useful clue backward to every earlier knob? especially when a model has many layers. Do not learn the name yet. First, wonder how you would make the blame travel backward. Before we leave, rebuild the idea without technical vocabulary. A model makes a prediction. We measure how wrong it is. The local slope tells us which nearby direction raises loss, so we move the other way. The learning rate controls how far we move. Tiny steps can be painfully slow. Huge steps can overshoot or diverge. Balanced steps make steady progress. We repeat until improvement becomes negligible. If a trial makes loss worse, a safety check can reject it and retry with a smaller step. And remember, downhill means lower loss, not always left-right or a smaller weight. Now the transfer question. If a completely different model has adjustable knobs and a measurable mistake, which parts of this loop still survive? If your answer is predict, measure, find a local clue, take a controlled step, check, and repeat. Then you have rediscovered gradient descent. If this is how you want to learn AI, subscribe and join us. Like the video, so more curious minds can find the series. And tell us in the comments what clicked, what was unclear, and what we should improve. Your feedback will shape the episodes that follow.